So the ugly number is another question which we have discussed already, and in that we found out that if we just do three main things to find out whether a number is ugly or not. So what were the three main things? We keep on dividing with 2 until it is divisible by 2, we keep on dividing by 3 until it is divisible by 3, and keep on dividing by 5 until it is divisible by 5. Now after this, whatever the remainder we have, if it is equal to 1, we say that it is an ugly number, because this number would have been of the form of 2 power x into 3 power y into 5 power z if after all these operations the final remainder is 1. Now we need to find out the nth ugly number. They have given us n and we have to find out the nth ugly number. We know that the first ugly number is 1, but now should we go and try for each, say 2, and try to search if it is an ugly number? Okay, we can do that. It will be of log of 2 to the whatever this m is plus log of 3 of m plus log of 5 of m. So these are the three things that will happen for each and every number, right? So that is the maximum of time complexity for each number. Now we need to search for n lucky numbers, which mean ugly numbers, which means that there are many non-ugly numbers also in between for which these all operations will have to do. So for n, it is something like n plus f, which will be equal to k. So that k into logarithmic of this time complexity, let us say just m. Now k log m will be our final time complexity if we do in the brute force. So brute force is not good, we cannot be doing that. For each of the value we cannot check it is very bad. But even after that, if we say, right, that we have reached a number, say 12, now we have checked for 12 and then we can get if that 12 is not, right? So what can we do better? We can just store some things into the memory so that we can just know that the next lucky number is something related to that. So what is the characteristic of a lucky number that we need to find out? That the nth lucky number is either n minus 1th lucky number into 2 or n minus 1th lucky number into 3 or n minus 1th lucky number into 5. So some number into 2, 3 or 5 is giving me the nth lucky number, that is for sure, right? So we will use this condition. This is the main observation or condition that we need to remember over here, that we need to fill it up while we are going forward. Fill up the n numbers that we need. Now what we mean by that, first we fill 1, then for 1 we know that the next lucky number will be found by this only, so we just put in 2, 3, 5 also. Now the next lucky number will be based on these. Take 2, so 2 into 2 is 4, 2 into 3 is 6, 2 into 5 is 10. Now put these, because of 2 these came. Now because of 3, I will know that 3 into 2, 3 into 3 and 3 into 5 will be my next set of lucky numbers, which can be found via 3. But the only problem is over here, that these are not in a sorted order. How to solve that? Take a set, y set, 1 for sorted. Second thing, we do not want duplicates. Now 3 into 2 and 2 into 3, these two both give 6. If I were to choose a vector, in which I would be adding and then just sort it at last, it would have been bad, because 6 would have come multiple times. So we can just use a set for that reason. So what were the two reasons? We need sorted. 1, 2, we need non-duplicates. I mean uniques. Right? We can just look at the solution now, what we'll be doing. So suppose if I wanted to find out the third in this, right? What would be my third? After rearranging this, I would have found out that 0 at the 0th position is the first one, second is second, 3 is 3. So my third lucky number, ugly number would have been 3. We can just look at the answer, what we are doing. Considering a set, inserting 1 into it, and then this is the main variable that is storing the answer which will be returning at last. This variable just stores the first array element at first, right? Because that is the first ugly number we know for certainly. Now if n is greater than 1, right, or n is even 1, then this, if n is 1, then this loop will just exit out. If it is greater than 1, then for each next subsequent one, we are just inserting all the possible values, all the next possible values into a set and rearranging them. So what this becomes, first it will have 1, then in the next step it will be 1, 2, 3, 5, but we are erasing this, right? So it will be 2, 3, 5. In the next step we'll be erasing 2, and then what will come in picture is 3, 4, 5, 6, 10. This will be in the picture after the second step. First step, second step. Now the third step, 3 will be taken into contention, and then 3 will be deleted. Now whatever we are deleting, right, whatever we are erasing, every step we are erasing one ugly number. So in the first step I'm erasing the first ugly number, in the second step I'm erasing the nth lucky number. So we can just store it in this current answer value, whatever we are erasing, and then insert the next set of ugly numbers. At last what will we have, because this loop runs for n times, we will have the nth lucky number in our current answer. Now we could also have used a priority queue, which is a better approach than a set, because it will just handle the best, or the what we'll call the minimum of all the lucky numbers into a min heap, and then O of 1 time will be taken to get it. So but overall both will have almost the same time complexities of order of m into n log n, because for every insert that we take into a set, it will be a log n operation, right? And we are probably inserting how many? N maybe into the set, right? It will be greater than n, of course, but high level it is just n log n kind of a thing. So the next approach is even better. At every step what we were doing is we were blindly pushing these into the set. Then when we are taking this out, we were pushing 2, 3, 5 into the set. When I was taking this out, I was just pushing 4, 6, 10 into the set. Do we even need this? We don't. What I want to know is if I can choose one and then choose out of 2, 3, 5, what will I choose? I will choose 2. Now what I will do is, I know that this will have another number for my contention. So 2 will give me 3 values, 3, 5. These 3 values will give me their next successor, or the next ugly numbers. Now it was 2, the next ugly number that this can give me now is 4. The next ugly number that this can give me is 6. The next ugly number that this can give me is what? 3 can give me 9, 5 can give me 25 also, right? 5 can give me 10 also, 3 can give me 6 also, right? So all these things. Now what we can consider is we can somehow intelligently manage this. What we'll consider now over here is we'll take a vector only. We don't need a set also over here. We'll just take a vector. In that vector of ugly numbers, we'll just initialize it with n. First insert 1 into it because we are sure of it. Then the next number that we know that will go into the vector, right? What will that be? So now we'll have 3 variables as ends, which will have the index of 2, index of 3, index of 5. These 3 indexes will be the indexes in this array. So now this array has 1, 2, 3, 4. Now this indexes array, right, will have this only. Now suppose index 2, index 1, index 3 and index 5 all are at 0 at first, right? If all of them are at 0, what do we know? What I have taken over here, I could have also taken it as 1, 1 and 1, and then this step would have gone down. Before doing the index plus plus, I would just give the whatever is next to, and then I would have incremented the index, right? But yeah, it is giving the same output regardless, so we can just consider this only. Now if I see that these indexes, right, or index 2, 3, 5 are over here, next step what we'll be choosing is who is the successor for this one. So we know that out of these 3 things, the next 5s, what are the contenders? 2, 3, 5. What we'll choose is the minimum of all these 3, which is 2. We put 2. Now still we have 2 contenders over here. From 3's palette and 5's palette, another contender joins this list. After 2 goes away, it will be 4. Why it will be 4? Because the index at which 2 was will be incrementing this to here, right? Now we will for sure know what is the value that needs to be inserted into it. Now if it was 2, but what will we be adding is the first vector, right, that we have chosen. In that vector we have already populated it with 1. All these variables have indices at here. Now when we have chosen that 2 is our next successor, I'll just move to 2 to here, right? I will add it into the vector also. No. But just before adding it to the vector, what I am doing is I'm finding out what is the minimum of these things. After that only I'll be able to put it into the vector. But after doing that, I know that 2's contentionship over in this thing is over now. Now it will just move over here. So 2's index will be over here. In the sense it will point to this index. So the next variable that this 2 will be giving us for contention will become 4 because of this. So now 2's contention is giving me 4, 3's contention is giving me 3, and 5's contention is giving me 5. So out of these all 3, now again I will choose and put something into the vector. It will be 3 because this is the least. Now we know that 3's contention is over here, and then so it will move it to this index. And now for 3's contention, this will go away and 6 will come inside it. because 3 into 2 is 6 into contention. Now again I will follow the same thing. Out of 4 comma 6 comma 5, 4 is the least. I'll put 4, and then 2's contention is over here in this index. Wherever it was, it will go above. 2's contention comes here. Now this into this, which is again 6, will go into the contention part. Now either to push it into the contention part, we can just maintain the array. If, like in the previous case, but do we need to? We actually don't, because we already have the indices, right? So what we are actually doing, we are finding out whatever minimum was there, and if it coincides with this, move this index also by 1, move this index also by 1. So the next contention elements, what they'll be giving, so the next element will be 5, right? And then 5 will have the next one, which is 10 into contention. Now comes the real case. When 6, 6 and 10 is present, then what we are going to do? Now what we are going to do is, out of these 3, what is the minimum? Minimum is 6, but what are the values that will increment for indices? For 2 and 3, both contention is 6. Now if I put 6 over here, I have to move 2 also, I have to move 3 also. What I can do over here now is, if the contention of 2 is over, which means next 2 was equal to ugly number of I, then I can just move the index of this 2 and then add it also. But the same thing needs to be done for next 3 also, right? If these 2 are also same, right, then over here also index 3 also should be plus. That is the thing. And then insert whatever the next contentions were there from each of the 2 and 3. So the same thing over here we are doing, over here we are doing, over here we are doing. We are incrementing the index, first point, second point, we are just new contender out of the 3. So we are progressively filling this array, and after n operations, we can say n operations of pushbacks. So the first pushback was over here only, in the sense that we are filling the first one. So how many will be left is n minus 1. So in this, we can just run the loop from 0 to n, right? In the first case we did that 0 to n, but over here it will be 1 to n, because we need to take care of all these values wherein n is not inclusive, 1 is inclusive. So from here till n minus 1 we'll have to fill in the values, so that total there are n values, and then return whatever n minus 1th part is present, element is present.